Hello everybody, so this is continuation of the air quality unit, and I wanted to spend some time thinking about greenhouse gases. Now the most common greenhouse gas that you probably have heard so much about is carbon dioxide. And we have a record for the last 400,000 years of how much carbon dioxide has been in our atmosphere. How we know this is from Antarctic ice. The Antarctica has been, at the bottom of the planet, gaining ice for a long time, and we have ice that is about 400,000 years old. So we can actually drill down there, look at the tiny little air bubbles, and see how much carbon dioxide is in that air. And we can actually, there's just tiny little needles that are pulled out, and then they can figure out how much carbon dioxide was in there. This is also through a different way. Actually, we can look at the stable isotopes of oxygen and figure out the temperatures, but I'm not really going to get into that. Now, we have been directly measuring the CO2 in Hawaii, on the top of a mountain in Hawaii, on the Big Island, Mauna Loa. There's an observatory, and they figured that this would be a great place to start measuring carbon dioxide because it's at like 14 or 15,000 feet, and it's not exposed to a lot of human impact or like industry or anything. It's a good place to measure the amount of carbon dioxide, and we've been measuring that since the 1960s. So what we can see is since the 60s, where we've directly measured it, it's definitely gone up. And right now we're somewhere above 400 parts per million. It's much higher than it has been in the last 400,000 years. So I want to spend some time thinking about how carbon dioxide actually fluctuates on the planet. So this starts with looking at the map. Now, what I want to say is that the majority of land is in the northern hemisphere, and that might not seem super apparent right now, but what I would say is look on this map at the size of the United States, okay? And look at the size of Antarctica. Because this is a projected three-dimensional spherical object on a two-dimensional surface, there is some distortion. So if you were to actually project the United States on top of Antarctica, Antarctica is, certainly bigger than the lower 48, but it's not as big as this map would, makes it. And then, so really, there's only three large land masses. So land masses that have plant life. Then that'll become apparent why we need to figure that, right, in a second. There's just really not very many plants down in Antarctica. There are some, but really not that much. So we've got Australia, part of Africa, and then a decent amount of South America. But in comparison to size, like North America is much bigger than South America here. There's a decent amount of Africa above in the northern hemisphere, and then Asia is just huge, right? So why does that matter? Well, because the majority of land is in the northern hemisphere, think about the northern hemisphere summer. What's happening? All the plants are going through photosynthesis. Photosynthesis sucks up carbon dioxide and releases oxygen. So because you have a net in the northern hemisphere summer, so like June, July, August, right? You've got the northern hemisphere sucking up a lot of carbon dioxide. Then in the northern hemisphere winter, you've got lots of decomposition going on. So think of, we've got a lot of snow and everything is dying, and there is, I shouldn't say everything is dying, right? A lot of plants are dying, annual plants, and then, so there's a lot of decomposition going on, which releases CO2. So we kind of have this flip-flop. When we think of just the northern hemisphere, we can think of the CO2 getting sucked up during the summer and released during the winter. Now, that's not to say that, during northern hemisphere winter, carbon dioxide is not being sucked up in the southern hemisphere. It's just that because there's so much more land in the northern hemisphere, this difference between the summer and the winter is bigger than in the southern hemisphere. So that's what's driving the this pattern that we see, where CO2 concentrations throughout a year will go up and down and up and down. So we have northern hemisphere winter, right? And then spring comes along, we have high CO2 concentration, spring comes along, carbon dioxide goes down until we get to somewhere maybe like September, October, where the northern hemisphere, basically photosynthesis isn't going on anymore, and plants aren't sucking up that carbon dioxide, and they start to decay and release a bunch of carbon dioxide into the atmosphere until over in the we repeat the cycle again. Now this is what would be the pattern if we weren't burning so many fossil fuels. But we are using a bunch of oil, a bunch of coal, a bunch of natural gas, and what we see for carbon dioxide is no longer this thing where we have a flat, oscillation, but we have an oscillation that is increasing. So, the low point in 2000, or the high point in 2004, is, just 4 years later is pretty much already, the low point in the year is already higher than that. So what we're seeing is CO2 concentrations are just continually increasing. And these are those data from the observatory in Hawaii, basically pretty much most of the data. And what we can see is we've had this increase. Yes, we've had, that fluctuation, that earth breathing here, due to the photosynthesis in the summer, but it's also going steadily upward. So let's look then and see what it is, the most recent data set. And there we go. The atmospheric CO2 concentration as of for April 2020 was 416 parts per million. Okay, and so if we look then at, back at this older data where it's back at 2010, it was only at 380. So just 10 years ago, we've increased the CO2 concentration by 20 parts per million, which is quite a bit when you think about it. When you think about like the percentage of that is quite a bit. So why does this matter? What does CO2 do? And you've heard about the greenhouse effect, I'm sure, but think of what happens when you park your car out, in a parking lot, or it might be even like a relatively cold day. It might only be 60 degrees outside. You park your car in a parking lot. What happens is the sunlight enters through the windows. It gets absorbed by the seats of your car. That heat then comes out and radiates out and gets reflected back in. The heat can't get out the windows. Only the light can. So the same thing is happening then, but on a global scale. So solar radiation will hit the Earth's surface. It'll be turned into heat, and some of the heat goes back into space, but a lot of it is then reflected back down, just like the windows in your car. And the more carbon dioxide we have, the more of that heat is reflected back down onto Earth. So when we have a scenario like this, what we can see is the CO2 concentration that we see here is very much reflected in the temperature the temperature that we see. So when we have lots of carbon dioxide, temperatures go up. When we have not a lot of carbon dioxide, temperatures go down. So these are the data that we've taken, and we can see that yes, they're very messy data, but while CO2 has increased, temperature has also increased. So why is CO2 rising? Basically, it's fossil fuel use, right? That is the biggest thing. That's where about 90% of the increased CO2 comes from, and it's just, burning coal, releasing natural gas, burning oil, and making cement is also a big one in there. But 9% of that is due to of the increase in CO2 is due to land use change, and that is burning down forests for agriculture. It is plowing land for agriculture. It's mainly agriculture that is doing this, but that's where our CO2 is coming from. So what is happening is when a forest gets cut down, all that wood essentially is, well, let's say these trees are used to build houses or something. It doesn't really matter, right? Now that wood is not going to decay, but all the tiny little branches that are cut off are going to be, basically just left on where the forest was cut down from, and those things will decay. And also, there's a bunch of soil carbon dioxide in the soil then that will get released that would normally have been stayed there if the trees would have not been cut down. Now the same thing is if you take a prairie and plow it into farmland, what you're doing is what plants do are take carbon dioxide and put it into their tissues, right? So a grassland where the majority of the biomass of a plant is underground means that it's taking carbon dioxide from the atmosphere and pumping it essentially underground. When you plow over a grassland and turn it into a field that you don't have, for good portions of the year you don't have anything growing on that, that's a net carbon dioxide source then that will create that is where a lot of that land use carbon dioxide is coming from. Now there's other gases that do this too. Methane is 70 times stronger at reflecting heat compared to carbon dioxide, and this is, where does methane come from? It comes from basically cow farts and wetlands. So the increase of rice paddies, particularly in Asia and how they grow rice there, has made some increase in the methane production of the planet. Chlorofluorocarbons are also one of the strongest greenhouse gases. They're 15,000 times stronger than carbon dioxide. These concentrations are declining because we banned them back a long time ago in the 1980s, and those concentrations are declining. So there's some good news, but realistically, with that increase in carbon dioxide, that's all we're going to need to continue to be in a warming planet. So that's all I have for now. See you later.